Hi, so this is Team Pluto as a Planet. I'm Jared Riley. For our team, we have Corey Reyna, myself, Shannon Williams, and Dr. Colleen Bailey. So this is the introduction. So for the start of our project, we wanted to use drones to map Mars. What we found though is that 90% of the surface of Mars had already been logged and mapped. And so we moved to strictly focusing on weather conditions. For dust storms, though not as intense as seen on the Martian, there's still a huge problem for astronauts and also the equipment on the planet. This is given such as like having solar power on Mars and it covering those panels. With safety also being one of the 5 core values, launching and landing conditions are one of the most crucial considerations for a mission like this. As a team, we moved from drones to machine learning. We thought that this would stretch our ability into making something new that NASA could use, but also provide a tool that could be implemented on hopefully any one of NASA's platforms. For the dust storm locations. So we found a CSV along with Mars equator photos. In that CSV were provided centroid longitude and latitude, which is the center of the dust storm, as well as the squared kilometer, or area squared in kilometers, as well as the day, month, and year. Some of the information that we had to sift through was the solar day and also LS, the LS location, which the LS location is the position of Mars in relation to the sun and just how the sun is hitting the planet. In correlating that image to the CSV. So machine learning requires two main parts, a data set for the algorithm itself and then also the deep learning algorithm. In correlating that image, as I said, we were given longitude and latitude, and that was in degrees. And we also had the size of the dust storms. On the left-hand side, you can see that the longitude and latitude, or the degrees, was from 90 to negative 90 and negative 180 to 180. And then on the right-hand side, we have some of the code that we used to correlate those parameters to the actual image itself, mapping it to the pixel value. This is also where we found the information. It was provided on NASA's website. We found that the radius of Mars was 96.2. We ended up rounding up. It wasn't a huge issue with machine learning, and it ended up filtering any inconsistencies out. Again, like I said, we had the degrees from 90 to negative 90 and then negative 180 to 180 and converting that to pixels. And that was crucial in finding the dust storms within the image itself. Also in our data set, we started off by initially padding the photo. So on the left-hand side here, you can see that the black space around that image, that was our padding. And then we chopped that picture up into blocks. We gave a 0 and a 1, a binary output for either dust storm or no dust storm. To do this, also we used a bounding box. That's in the center photo here. We bounded out where the dust storm was in the picture. And then we passed that off to an MPZ file. What we found though is that the pictures after the padding were 24 million parameters and just computationally way too intensive. And so to fix this problem, we ended up masking the picture. That's on the right-hand side here. So a mask essentially creates it can be a box, a circle, or anything that you want. We used a circle, and then we zeroed in on the actual storm itself. Different pictures had different number of storms. Some pictures didn't have a storm, in which case we would take the entire picture. And then if the picture had multiple dust storms, we would take multiple pictures. After that, we would compress it and then save that to an MPZ, which ended up finishing our data set and roughly accounted for 90% of our project. Next, we move into the deep learning algorithm. For ours, we used a vision transformer. So in our proposal, we discussed using a CNN, a convolutional neural network, or an LSTM, which is a long short-term memory, or a mixture of both to do the prediction and classification. What we found though is that a vision transformer outperformed a traditional CNN model in both its efficiency and its accuracy. Instead of blocking our image, sort of like what I talked about and how we took and compressed it and masked it, and what we learned is that the vision transformer did a lot of this stuff for us, and I'll talk more about that. And it was also brand new, and so cutting edge technology in our eyes as it came out in 2021. So a vision transformer and how it works. It takes the patch of the dust storm and then breaks it into blocks or patches, and then puts those patches into a list, and then passes the individual patch through a transform layer. This is where the vision transformer really shows its superiority and is far more efficient and accurate than a traditional convolutional neural network. The patch goes through an initializer and then into the multi-head, and that multi-head takes the patch and it twists it and it looks at it through all different angles, and then assigns weights to that patch, which is what the machine learning algorithm will look at for its correlation for a dust storm or not a dust storm. After that, it puts the patches back together. And then what makes our vision transformer unique is we take and pass that then through a convolutional filter after. So the vision transformer, the output that we received, we were really excited and surprised at the accuracy of our model. And this is where it shows, again, it's just superiority to a lot of the deep learning algorithms that we've seen before. At only 160 to 170 epochs, we reached 100% accuracy and maintained that through the entire model. The epoch is how many times it cycles back through the model. At 170, we still had over 2,700 epochs to go. We passed around 3,000 epochs for the model and maintained that 100%, which really assured us as a team that we had not received a false positive, but also had a really strong data set, and that our classification was correct. So in the initial proposal, we believed that we would have roughly the course of a year. Though there was a huge time constraint, the team was extremely confident in its ability to learn, and we're still extremely confident, even with only a 3-month time span. This project was no small undertaking. We're extremely proud of the work that we've accomplished and also extremely proud of the results that we've received. Currently, we have classification for a dust storm being inside of an image. The next step is segmentation and prediction. And for the rest of this semester and moving into the next semester for the finalization of our senior design year, we plan to accomplish both of those. We also would just like to say thank you to NASA for the opportunity to do this. This was huge for us and just a really cool opportunity. And so we just again wanted to say thank you for the chance to work on something like this. Also, we wanted to provide a reference list for some of the sites that we had. This is where we ended up getting the learning model and also the pictures that we used from NASA and some of the data that we had.